Welcome to Heart of Mathematics. This is a second in two videos on fractal dimensions. Has some more examples of some fractals with a discussion on their dimensions. So let's look at two examples here, the Sierpinski triangle and the Sierpinski carpet. The difference between these two fractals, one starts out a triangle and the other starts out as a square. So the Sierpinski triangle is an equilateral triangle that has the middle quarter triangle removed. So you divide the triangle into 4 equilateral triangles. You take out the middle piece. As we can see here with the iteration, we take out the middle piece in white, and then every smaller black triangle, we take out its middle piece in white and continue down. So with the Sierpinski triangle, the scale, it takes the scale here, if this is a side length of 1, the scale here, this is a side length of 1/2, because it takes half the side to get the same distance. Their scale here is 2, and it takes 3 copies to build the next triangle, the next iteration. So if given it 1 original black square, it takes 3 black squares to build the next iteration. So our dimension here is natural log of 3 divided by natural log of 2, which is approximately 1.58. So this shape is not quite a 1-dimensional shape, and it's not quite a 2-dimensional shape. It's almost a little bit more than a 1.5-dimensional shape. Now with the Sierpinski carpet, it starts out as a square, and you remove the middle square. If you divide the square into 9 pieces, then you remove the middle 9th piece. So if we broke this square up into 9 pieces, so let's just draw this grid here. We were to break the square into its 9 pieces, we would remove that middle 9th of the square. So this means if we have unit length 1, our scale factor is now 3 because it takes 3 copies to build this. And our new number to build our squares, it takes 8 of the original size to build our squares. So our dimension ln of 8 divided by ln of 3 gives us 1.89. So the Sierpinski carpet takes up more space versus a Sierpinski triangle in the plane. So over the same amount of space, the Sierpinski carpet covers more of the 2-dimensional plane than the Sierpinski triangle, even though they're formed by the same iterative process. So let's look at the Cantor set versus the Cantor dust. So the Cantor set is built out of a line where you take the line of unit length 1 and you take out the middle third of the line. And every line after that, you remove the middle third of that line. So the number of pieces it takes to build the next segment is 2, because to go from the first iteration to the next iteration, it takes 2 copies to build the next piece up. The scale factor is 3 because it takes the scale of the next size down is 1/3 of the original size. So the dimension is the natural log of 2 divided by the natural log of 3, which is equal to 0.63. Notice the Cantor set has dimension 1 over the dimension of the Sierpinski triangle, natural log of 3 over natural log of 2, which I think is kind of cool. Now the Cantor dust, we take a square and we remove the middle third square on each side and the center as well. So we leave only the corners. So we take out 5 squares, the middle kind of cross pieces at each turn. So leaving only the corners, and there's several variations on the Cantor dust in the Cantor set, but we remove only the corners. So given that the initial side length was 1, the new side length is 1/3. So the new number of copies it takes is 4. It takes 4 copies of the original piece with a new side length of 3. So the new dimension is natural log of 4 divided by natural log of 3, which turns out to be 1.26. So this new shape is barely above the dimension of a line. Even though it started out as a square, we get pretty close to the dimension of a line in space. And that's kind of cool. And so fractals are properties or objects that have these sort of partial dimensional shapes. But sometimes a fractal can have a full dimension. We can have a space-filling curve. And these are known as, a particular one in general is known as the Hilbert curve. And for that, I'll leave you to see YouTube. Any questions? Just let me know.